Hello friends, today's question. A cylindrical vessel of height 500 mm has an orifice at its bottom. The orifice is initially closed and the water is filled in it up to height h. Now the top is completely sealed with a cap and the orifice at the bottom is open. Some water comes out from the orifice and the water level in the vessel becomes steady with the height of water column being 200 mm. Find the fall in the height of the water level due to opening of the orifice, and these are the parameters. So this is our 1.0 10⁵ Newton pressure, density is 1000, G is taken supposed to be 10, and neglect the surface tension. So in this question we are going to use, rather we can say we are going to start with using the Bernoulli's theorem, and then we are going to apply the Boyle's law to find out the fall in height. Okay. So initially we are given that the water is filled up to the height h. So let us suppose this is the height of the water h, and the height of the vessel is over 500 mm, and it is having a small hole or face at the bottom, and initially it is sealed from the top, and later on, as it is sealed from top, this orifice is opened and we get a slight reduction in the height of the water, and that reduction in the height of the water is said to be given as 200 mm. This is the reduced size of the, or we can say reduced height of the water, and this is 200 mm, and the vessel is sealed from the top, and this is the orifice. So let us call this top as position A, and the orifice, or we can say this lower part, let us call this as position B. Okay. So this is our initial condition, and this is our final condition. So we are going to use Bernoulli's theorem for this final condition, and that will be helping us in order to find out the pressure at the top, and then we are going to use the Bernoulli's principle in order to find out what will be the fall in the height. Okay, so let us start with the Bernoulli's theorem, and we say for final condition, we say for point A, which is top of the water column, top of water column, and after the water has been stabilized, because it is given in the question that there is a steady height of the water column. Okay. So top of the water column after water stabilizes. And in this condition, the height of the water for this, let us call that HA. So we are going to call this as HA, which will obviously equal to 200 mm. So we get HA V is about 200 millimeter, and at this level let us call the velocity as VA. So we call the VA velocity of the water. Velocity of water, and here let us call that pressure as PA. PA is pressure at point A, and this is the velocity of water at point A, and this is the height of water which we said is at point A. So therefore we can use Bernoulli's principle, Bernoulli's theorem at point A. Bernoulli's theorem at point A. Pressure at point A plus half rho VA square plus rho GHA should be equal to constant. And we can say that the velocity is approximately equal to 0 because the water is stabilized. So we can write VA is approximately to 0. Water level is stabilized. Therefore we can write this equation that our PA plus rho GHA is equal to constant. Similarly, we are going to use Bernoulli's theorem at this bottom level B. So you can say for point B, which is at the bottom of the orifice. At the bottom, you can say, of the tank near the orifice. At the bottom of the tank near to orifice. Here we call that you can say velocity of the water as VB. VB, velocity of water. Velocity of water at point B. PB, we call that pressure at point B. Pressure at point B, and HB, we call that height of point B. Height of point B. So once again, using Bernoulli's theorem, we can write PB plus half rho PB square plus rho G HB will be equal to constant. So here PB will be equal to P naught, that is our atmospheric pressure, VB is approximately equal to 0 and HB is also approximately equal to 0. So from here both the terms from VB and HB are 0. So we can say our PB is equal to constant. So therefore we have two levels, A and B, and according to Bernoulli's principle, the Bernoulli's theorem which is applicable at level A should be equal to Bernoulli's theorem that is applicable at level B, because there is only difference in level. So that is means everything sum of each energy is equal to constant. So we can write thus PB, or let me write PB first. PB is equal to our PA rho G HA, and PB is nothing but our P naught. So we can write this is equal to P naught. Therefore we can say our pressure at point A will be equal to P naught minus rho G HA. We substitute the values. P naught atmospheric pressure is given at 10⁵ minus density is 1000, gravity is 10, and height is given as 200 mm, which is 0.2. And from here we get that pressure at point A is equal to 98 into 10⁵ Newton per meter square. So we were able to find out what will be the pressure at point A. Now we are going to use Bernoulli's theorem, Boyle's law to further for further calculation. And for that we are going to use these two figures now. We are going to make a comparison of Boyle's law. This is our initial condition and this is our final condition. So let me redraw the figure again. So H is the height, 500 mm is the total height of the, and the final condition, the water level has reduced to 200 mm, and cylinder that tank height or vessel height is still 500 mm. So like I said, this is our initial condition. So we say we have here initial pressure and initial volume, and this is our final condition. So we have here final pressure and we have here final volume. So from here itself we can see total height is 500, the liquid level is 200 mm. So we can calculate this height will be our 5 minus 2, that is our 300 mm. So we can use Boyle's law for initial and final condition. Let me write here, this is our initial condition and this is our final condition. And keeping in mind that we are going to use the Boyle's law for the trapped air, not for the liquid. Okay. So I'll write this here. You can say applying Boyle's law for the trapped air of the trapped air. For the, we can say initial condition, Pi multiplied by Vi is equal to Pf multiplied by Vf. Please keep in mind that here V is the volume, not the velocity. Okay, V is the volume. Okay, previously in the Bernoulli's theorem, V were equivalent to velocity. So Pi is our initial pressure of air, and in the question itself it is mentioned that the orifice is initial closed and water is filled up to a height h. Now the top is completely sealed with a cap. So as the top is completely sealed in cap, this particular portion will be having the air at only the atmospheric pressure. Okay, so we can say Pi is the initial pressure of the air, or we can say that will be equal to atmospheric pressure, and the atmospheric pressure is given as 10⁵ Newton per meter square, and Vi is our initial volume. So this height we can say will be equal to 500 mm minus h. This is 500 minus h, because we are interested in only the air trapped. Okay. So from here we can say that Vi is the initial volume of the trapped air, and that will be equal to A multiplied by 0.5 minus h, where A is the, you can say, area of the cylinder, cross-sectional area rather, area of the cylinder. Pf is the final pressure. Pf is the final pressure of the trapped air. And please keep in mind that we just calculated the pressure at point A, or we can say at level A. Okay, so we calculated Pf, and Pf will be equal to Pa, which is equal to Pa, and Pa we found out is 98 × 10⁵, and Vf is the final volume, of the trapped air, and that will be equal to A multiplied by, here we just, this is our 500 minus 200, that is 300 mm. So this will be A multiplied by 0.5 minus 0.2, that comes as A into 0.3. So we can now equate it. Pi is equal to Pi multiplied by Vi is equal to Pf multiplied by Vf. So Pi was our 10⁵ multiplied by Vi is our A 0.5 minus h is equal to Pf is our 98 10⁵, and this is our 0.3. So this A cancels with A, and we can say from here, or we can say just sort it out, we can write 0.5 minus h will be equal to, this comes 98 10⁵ multiplied by 0.3 divided by 10⁵, which comes approximately equal to 0.294, or we can say our h is equal to 0.5 minus 0.294, and that is equal to 0.206, or we can say 206 millimeter. So we were given rather that the initial height, we just calculated h, so it means initial height of the water came out as 206 and final height is given to us is 200 mm. So therefore from here we can say that initial height of water is 026 mm and final height of water, it was given as 206 mm. So fall in height of water, fall in height of water, we subtract them, this comes as 6 millimeter, and that was asked in the question. Find the fall in height in millimeter water level due to opening of the orifice. So the fall in height is our 6 millimeter. Okay. This completes the question. Thank you.